Alright guys, this is our first Flip the Classroom lesson. It's going to be on function analysis. We're going to break this up into 3 videos, and this is the first of those 3 videos. So, we talked a little bit about functions before. We've said that a function is a rule that assigns every input one output. When we're talking about function analysis, we're talking about identifying trends and characteristics of function values on the xy axis. Well, if we're on the xy axis, we know that our inputs are going to be x values, and we say that our outputs are function values, which we measure on the y-axis, making them really the y values of the function. So we're going to be using y values of the function and function values interchangeably. The way we want to think about this is the x-axis is the axis of inputs for all functions. And what makes those functions unique is how they react to those inputs, or those function values, which of course are measured on the y-axis. So when we're talking about identifying trends and characteristics, a lot of times we're saying what x values or inputs are causing the trends and characteristics of our function values. What we're going to start with is where functions exist on the xy axis. So let's talk about what it means to exist on the xy axis. If we've got a point that exists on the xy axis, it has an x value and a y value. We'll call our x value A and our y value B, and they come together to give an ordered pair that is the position of that point on the xy axis. Well, the x-axis and the y-axis are both real number lines, and then what that means is that the A value and the B value both have to be real numbers. So when we're talking about the rule of a function, generally what we're going to be doing is talking about some equation that takes x values, processes them, and is going to give some function values. And if those function values exist on the xy axis, that means that the x values we process are giving us real number y values. So what we're going to say is a function exists on the xy axis for all x values that give real number y values. We call these x values the domain of the function. So when we're talking about domain, we're saying a domain is all inputs. We might say valid inputs, right? Inputs that give us, that the function is able to process to give us outputs for. In general, we say that the domain is all the inputs for a given function. On the xy axis, of course, we're talking about the x values that give real number y values, as we stated above. One thing we can notice is that all polynomials have domains of all real numbers. And what this means is a polynomial is able to process every single x value on the x-axis and give a real number y value. Well, why is that? Well, let's look at how we define a polynomial. We say that a polynomial is any function that can be written as the sum of terms with x values or independent variables raised to integer powers. This should be positive integer powers with a real number of coefficients. So right here, what we want to think is we're basically summing a bunch of terms that have x values raised to positive integer powers with real number coefficients. So can anyone give us an example of a polynomial? Okay, so right here, so as an example, let's look at f of x equals x to the fifth minus 8x cubed minus 10x squared plus 1. Right here, what we're seeing is our real number x values plugged into our function, right? Immediately, those real number x values are being raised to positive integer powers, right? So they're being multiplied by themselves. So we're multiplying real numbers with real numbers. Then they're being multiplied by real number coefficients. We'd say the real number coefficient there would be 1, right? And then we're adding all of those real numbers together. When we multiply real numbers, we get real numbers. And when we add real numbers together, we also get real numbers. So in this case, we can say that the function is going to, any polynomial, right, is going to be able to process any x value and give us a real number y value. If we look at the graph of this function, what we'd see is something that looks a little bit like this. And it's a rough sketch. You guys can graph it on your own and take a look at what it looks at. Something like this. And in general, what we're going to say is that this function covers the entire x-axis. So graphically, if we're identifying the domain, we're basically sort of saying that it's a function that's going to cover the entire x-axis. And as these two arms of our polynomial go up to positive infinity and negative infinity on the y-axis, what we're seeing is these two arms slowly eke out to positive and negative infinity on the x-axis. We can also write a domain of all real numbers in interval notation as the interval from negative infinity to positive infinity. So basically saying that's the entire x-axis. All real numbers from negative infinity to positive infinity incorporates all the real numbers. In general, what we're going to say is that most functions can process most x values and give us real number y values. So it's not really practical for us to look for all the x values that'll give us real number y values when we're looking for the domain. Instead, what we want to do is find the x values that will not give us real number y values and exclude those from the domain. And we've got two restrictions that are going to help us do that. So what we're going to say is our domain restrictions that we're going to look at first are going to be no negatives under an even root, and our second domain restriction is going to be no zeros in the denominator, right? So let's take a look at what this means. So let's say we've got y equals the square root of x. Well, what's it going to mean if I have an x value that will give me a negative under my even root, the square root? Let's say we've got negative a. So a is some negative real number. Well, if I plug that in, I'm going to get y equals the square root of negative a, which is going to give me the square root of negative 1 times the square root of a, which gives me I square root of a. And this is an imaginary number, which is not a real number. So right here, a square root is not able to evaluate a real number, a negative real number, and give us a real number output. So right here, when I'm identifying the domain for a function like our f of x right here, what I want to do is identify the restriction. So basically, I'm going to take the expression in the function that could potentially violate this restriction right here and solve for all the x values that will violate this restriction. So right here, I've got x minus 5, and I'm going to say, where is this guy going to be less than 0 or negative? And then I'm going to say I can't have those x values. Now I'm going to solve this like a regular inequality. So right here I'm going to say plus 5, and I get x cannot be less than 5. So right here my domain would be the x values on the x-axis that are not less than 5. So right here, from 5 to positive infinity, right? That would be the domain of this function right here. In general, what we want to think is that we can have an x value that will give us 0 under an even root. So right here, if I plug in, not 0, if I plug in 5, right, I'd have f of 5 equals the square root of 5 minus 5, which is the square root of 0, which is 0, right? So in general, right here, it's not 0 that we're worried about under an even root, because the square root of 0 is 0. That's a real number. It's any negative number under an even root that's going to give us an imaginary number, and that's what we have to watch out for. Okay, so right here, let's look at our second restriction. Second restriction says no zeros in the denominator, And of course, right here, if we've got y equals 1 over x, if I let x equal 0, then my y value is going to be 1 over 0. I can't divide anything by 0. Can't divide anything by 0. So this is going to make me undefined for x values that give me 0 in the denominator. And again, what we're going to do right here when we're solving for the domain of a function that could potentially give us 0 in the denominator for some x value is we are going to take that expression in the denominator and find the x values that will violate that restriction and say we can't have those x values. So I can't have any x value that will make x plus 2 equal to 0. And I'm going to solve this like a regular equation. So I say minus 2, and right here x cannot equal negative 2. So when I extract 2 from the number line, say I can't, or negative 2 rather, from the number line, saying I can't have that number, I would say my domain would be negative infinity to negative 2 union with negative 2 to positive infinity. And that would be the domain for this function right here. So right here, what we're going to do is give some of these a try. Looking on our next page, I want to sort of talk a little bit about the strategy here. We've talked about how we're going to solve for those domain restrictions, but we want to talk about how we're going to start thinking about them as well. Right here, if we've got a function, in general what we want to do is sort of scan that function for places where we might have one of our domain restrictions. Now, my first function right here, y equals 5x to the fourth plus 3x squared minus 7, as I scan this, there's nowhere where I could, an x value could give me 0 in the denominator or a negative under an even radical. So because I'm not violating either one of those two restrictions, I'd say my domain is all real numbers from negative infinity to positive infinity. And that, of course, makes sense because this is a polynomial, which we've already said can process every real number on the x-axis and give us a real number y value or an ordered pair that will define the function at that x value. So right here, if I look at my second function, I've got x over 2. But there's no way that this guy can give me 0 in the denominator because 2 is not going to equal 0. I've also got my second term, 5 over x minus 3. There is an x value that will make x minus 3 equal to 0, and we can solve for that by adding 3 to both sides and sort of seeing that x cannot equal 3. Then our domain, of course, is going to be negative infinity to 3 union with 3 to positive infinity. Okay, so I want you guys to try these two problems right here, and we're going to come back in a second and give them a shot. So pause the video and give these a try. Okay, so let's look at these guys. All right, so first off, for A, we can see that we've got x minus 1 in the numerator, but we're not concerned if the numerator equals 0. We're okay with that. It's only the denominator we have to worry about equaling 0. So we're going to take this expression in the denominator, and we're going to look at what x values will make it equal to 0. So right here we can set this guy equal to 0, factor. We get the two zeros of 1/5 and negative 4. Those are the two values we're going to exclude from our domain, sort of pull out of the x-axis, and we get these three intervals. We get the interval from negative infinity to negative 4, the interval from negative 4 to 1/5, and the interval from 1/5 to positive infinity, and those three intervals make up the domain of the function. These are all the real number x values that we can plug in that will give us real number y values. For our second function, we've got a little bit of a tricky one. Right here we've got x to the 1/2 plus x minus 5 to the 1/3. Now immediately this is a little bit tough to look at to determine a domain from, but what we can do is change these fraction exponents to radicals, right? So the 1/2 power becomes the square root, and the 1/3 power becomes the cubed root. Right here, what we can do is see that we have an even root, the square root, and we have a cubed root, an odd root. We don't care if we have a negative under an odd root. Our function can process a negative under an odd root. It cannot process a negative under an even root. So the only restriction we have to worry about here is x being less than 0, which gives us a domain of 0 to positive infinity. So that would be the two domains for these guys. What we want to do now is go back and look a little bit at the graphs of our functions and talk about the domain graphically for the two functions on the previous page. All right, so for our f of x, right here we've said that we can process 0, right? So the x value that gave us 0 was 5, and when we processed that x value, we got 0, right? And right here, that gave us, that's going to give us the ordered pair 0, 5. And what we're seeing from the rest of this function is basically 1/2 of a sideways parabola that opens up onto the x-axis. And it's pretty easy to see that this function is covering the x-axis from that first function value we get at x equals 5 all the way out to positive infinity. Right? So it's easy to see our domain here. I want to talk a little bit about what we're seeing from this guy as we approach that hole in the domain of -2, that single x value that we can't have. So right here, what we want to see is that we have a rational function, or a function that has a variable expression in the denominator. And right here, what that's going to mean is the x values that give us a larger denominator are going to give us smaller outputs, and the x values that give us a smaller denominator are going to give us larger outputs. So let's start with plugging in x equals, let's say we're going to plug in x equals 1. When we plug in x equals 1, we get 1 plus 2 in the denominator, which gives us an output of 1/3. So right here, we've got something pretty close to the x-axis. As we get a little bit closer, let's plug in 0, we get 1/2. So an output that's a little bit more. And right here, as we get even closer to that x value of -2, let's say we go to -1. Now right here, when we plug in -1, we're going to get 1 in the denominator, which is going to give us 1/1, or an output of 1. Now, we're seeing a slight increase as we approach the whole of -2 by integers. What's going to happen when we start processing x values between -1 and -2? Right here, if we plug in -1.5, that's going to give us 1 over 0.5, which is going to be 2. So already we're jumping up one integer just in half an integer on the x-axis, within half an integer on the x-axis. What's going to happen when we plug in something like 1.75? Well, right here, that's going to give us 1 over 0.25, which is an output of 4. So already, right here, within half an integer increment on the x-axis, we're seeing a jump of 2 units. What happens when we get really close? We get really close, let's say we plug in -1.99. Now when we plug in -1.994x, we get 1 over 0.01, which is giving us an output of 100. We're already off our graph. So basically what we're seeing is the closer we get to that hole of -2, the smaller the denominator gets and the larger our outputs get. And the trend we're seeing here is called a vertical asymptote. And basically, our graph is going to look like this. We sort of see our function values jump up to positive infinity. As we approach from the negative side, we're going to see the same trend, but those x values that we're going to plug in are going to be larger than +2, so we're going to get negative outputs, and we're going to see our function values go down to negative infinity. And this is a vertical asymptote. And we would say that we have a vertical asymptote at x equals -2 here. Now, in general, when we're solving for holes in the domain, we're basically going to say these are the x values we can't have. But these holes in the domain, the holes in the domain that give us 0 in the denominator, are going to be some of the ones that give us vertical asymptotes. So for us to solve for vertical asymptotes, we're going to be solving for those x values that give us 0 in the denominator, and we're going to be saying x equals that x value, and that's where the vertical asymptote is happening on the xy axis. Okay, so we want to talk a little bit about combinations of restrictions. I'm going to go ahead and show you guys this first one, and then I'm going to let you guys try the second one. If you want to try both of them, you can pause the video right now. Okay, so right here, I'm scanning my function for possible restrictions. This one's got a bunch of them. Right here in my numerator, I can't have x plus 2 be less than 0. And in my denominator, I can't have x minus 2 equal to 0, right? So basically, the two restrictions I'm going to have is x cannot be less than -2, and x cannot equal 2. Now, when I'm looking at a combination of restrictions like this, what I like to do is map it out on the x-axis. It's just a little bit easier to see. And the first thing I'm going to do is I'm going to look at that inequality. Right here, that inequality is telling me that I can't have anything less than -2. So from -2 on are x values that will be okay for the square root of x plus 2. Now, the second violation we have is x equaling 2 in the denominator giving us 0. So right here what we're going to say is we also cannot have x equal to 2. So right here what I've got is the domain as the two intervals from and including -2 to 2 union with 2 to positive infinity. And that would be the domain of this function right here. So again, you guys can pause the video right now and give this one a shot. We'll come back and do it in this. Okay, so when I look at this second function, I've got a couple things to worry about right here. When I look at the two factors in my denominator, I've got x plus 3, so x plus 3 cannot equal 0, so we know x cannot equal -3. Right here, I've got the square root in my denominator. I know I can't have a negative under an even root, so x cannot be less than 0, but because this factor is in the denominator, x also can't equal 0, right? Because if we get 0 right here, that's going to multiply this factor and give us 0 in the denominator. So immediately, what I'm saying is the inequality, so what I'm going to look at first, and right here, that's telling me that I can't be equal to 0 or less than 0, so I'm going to have the interval from but not including 0 all the way out to positive infinity for this first restriction. My next restriction is that x cannot equal -3, but -3 is a x value that we have already excluded from our first restriction. So right here, we don't have to worry about it, and we can say that our domain is going to be from 0 to positive infinity, and it's going to look like that.